The universe continues to baffle and intrigue humanity, and for astronomers scattered across the globe, a recent discovery has ignited both fervent excitement and profound bewilderment. They have detected an extraordinary visitor, one that traversed the vast, silent expanse between stars for a staggering duration, potentially spanning millions, even billions of years. This lone traveler, having journeyed through the absolute void of interstellar space, has finally arrived within our immediate cosmic neighborhood, landing precisely within our solar system at this very moment. This phenomenon is the subject of intense scrutiny. The object, designated 3IATLAS, recognized as the third confirmed interstellar visitor ever observed breaching the boundaries of our solar system. What renders 3IATLAS particularly astonishing and genuinely perplexing is its behavior. It is acting in ways that fundamentally challenge and contradict the established understanding scientists possess regarding the nature and characteristics of comets. The object's trajectory, composition, and activity defy conventional explanations derived from studying celestial bodies originating within our own solar system. This defiance of expectation has pushed the boundaries of existing knowledge and sparked vigorous debate within the astronomical community. Within this landscape of scientific inquiry, a significant division of opinion has emerged. While the overwhelming consensus among researchers firmly asserts that 3IATLAS is in fact a natural comet, an icy fragment ejected long ago from another star system, one highly prominent figure from Harvard University has dared to raise a question that many colleagues seemingly hesitate to voice openly. This distinguished astronomer poses a radical, almost unthinkable proposition. What if 3IATLAS is not a natural comet at all? What if this enigmatic visitor from the stars represents something entirely different? What if its presence here is not the result of random cosmic drift, but rather the deliberate act of intelligent design? What if it was sent? Before dismissing this line of inquiry as the realm of fanciful speculation or unwarranted conspiracy, it is crucial to examine the tangible evidence underpinning this hypothesis. The data supporting these observations is concrete and derived from the most respected institutions in astronomy. Information gathered by NASA, the European Space Agency, the renowned Hubble Space Telescope, and a multitude of observatories spanning the globe. The phenomena associated with 3IATLAS, as recorded by these sophisticated instruments, are genuinely strange, exhibiting properties that current natural models struggle to fully explain. These anomalies form the basis for the Harvard astronomer's unsettling suggestion. This unfolding narrative possesses more unexpected twists and turns than initially anticipated.
The journey to understand 3IATLAS is far from over. The object remains active within our solar system, continuing its passage through space. It is still being observed, and each day brings fresh revelations, further deepening the mystery and compelling scientists to reconsider everything they previously believed about interstellar wanderers. By the conclusion of this exploration into its nature, one might well find themselves pondering the very same profound question that occupies the Harvard astronomer's mind. The mystery of 3IATLAS endures, a compelling enigma suspended against the backdrop of the infinite cosmos. The identity of 3IATLAS emerged from an unexpected observation during routine cosmic vigilance. On the first day of summer in the year 2025, a sophisticated automated telescope situated in the clear skies of Chile was scanning the heavens as part of the ATLAS project. This dedicated system primarily monitors for potentially hazardous asteroids whose paths could threaten our planet. Its sensors registered an anomaly, a seemingly insignificant point of light, possessing a magnitude of 20, an indicator of extreme faintness. Such dimness is beyond the reach of ordinary telescopes, requiring immense optical power just to discern a minute speck against the vast backdrop of space. The object resided approximately 4.5 billion kilometers from the Sun, adrift within the remote reaches of the outer solar system. However, astronomers swiftly analyzed the celestial body's movement. Within a single day, their calculations revealed a startling truth. The trajectory defied the familiar patterns of solar system inhabitants. Instead of tracing an elliptical loop, the stable orbit that binds objects within our Sun's gravitational embrace, the object followed a distinctly hyperbolic path. This crucial mathematical distinction, this deviation in shape, carries profound significance. An elliptical orbit condemns an object to perpetual revolution around the central star, destined to return eternally. Conversely, a hyperbolic trajectory signifies a transient passage. The object arrived from afar, traversing our system without becoming trapped in its gravitational well. By the second day of July in the year 2025, the international authority responsible for cataloging minor celestial bodies, the Minor Planet Center, officially confirmed the nature of this discovery. It was unequivocally an interstellar object, the third instance of such a visitor formally recognized by science. The first confirmed interstellar traveler, designated Oumuamua, had been detected in 2017. This initial encounter generated considerable intrigue due to its unusual cigar-like form and sparked speculation regarding its potential artificial nature. The second confirmed object, Comet 2I Borisov, was identified in 2019.
Unlike its predecessor, Borisov exhibited characteristics entirely consistent with those of a typical comet, generating significantly less controversy and debate. Now, 3IATLAS arrives, the latest cosmic envoy, the newest enigma gracing our solar system. Initially, scientists hypothesized that 3IATLAS was simply an asteroid, a fragment of rock and ice that had been ejected eons ago from some distant planetary system, forever cast adrift in the cosmic ocean. As the weeks progressed, and increasingly powerful telescopes focused their gaze upon this celestial visitor, astronomers began to discern unmistakable signs of activity. A faint, diffuse glow encircled its central nucleus, and a distinct short tail became apparent against the starlit backdrop. This was no inert celestial boulder tumbling through the void. It was, unequivocally, a comet. The intense solar radiation striking the object as it neared the Sun had begun to transform its icy composition. Water ice and other frozen volatiles within its nucleus were undergoing sublimation, transitioning directly from solid to gas. This escaping vapor, enveloping the core in a gaseous and dusty shroud known as a coma, and propelled outward by solar radiation pressure and the solar wind, generated the characteristic glowing halo and tail associated with comets. It was precisely during this phase of heightened activity that the most intriguing aspects of this object, designated C/2025 N1-Atlas, became impossible to ignore. Its photometric behavior defied easy categorization. Its luminosity fluctuated in ways unlike any previously observed comet. Furthermore, its orbital path traced through the inner solar system with an uncanny precision, seemingly governed by immutable celestial mechanics rather than the chaotic perturbations typical of most cometary orbits. Even more perplexing was the conspicuous absence of the early vigorous outcasting bursts that most comets emit when first exposed to significant solar heating at greater distances. This strange silence, coupled with its pristine trajectory, suggested profoundly that this object possessed inherent characteristics setting it fundamentally apart from the countless comets inhabiting our solar system. The very name assigned to this enigmatic traveler revealed its extraordinary story. The leading C/ designation classifies it as a non-periodic comet, indicating it does not follow a closed repeating orbit around the Sun like the famous Halley's Comet or others.
Instead, it was making its first, and likely only, passage through the inner solar system. The year 2025 signifies the specific period of its discovery. The N1 denotes its position within the discovery sequence. It was the first object identified during the first half of July within the systematic survey designated by the letter N.
In this case, ATLAS refers to the specific astronomical survey, the Asteroid Terrestrial Impact Last Alert System, that first detected its faint light. However, the most critical element of its title is the crucial I embedded within ATLAS, signifying its ultimate classification, interstellar. This marked the third confirmed instance of an object originating beyond the gravitational confines of our solar system that humanity had ever identified. Contemplating this fact demands profound reflection. Throughout the entirety of recorded human history, astronomers have meticulously cataloged millions of asteroids and comets within our own solar neighborhood. Yet only 3 times has an interstellar traveler been confirmed, a visitor whose journey spanned the immense gulf between stars. This singular event underscores the extraordinary rarity of such cosmic crossers. 3IATLAS possesses an inherent rarity that immediately sets it apart as profoundly special. However, what truly intensifies its intrigue lies in its colossal scale. Initial assessments indicate the nucleus, the solid, icy heart of this comet, could measure anywhere between 0.6 and 5.6 kilometers across in diameter. This represents an immense size for an object originating beyond our solar system. Should it reside near the upper bound of this estimated range, 3IATLAS would claim a place among the most substantial interstellar visitors humanity has ever registered. The significance of this considerable bulk cannot be overstated. Larger cometary bodies possess distinct advantages for surviving the harsh journey through interstellar space. Their greater mass makes them significantly more resistant to destruction by impacts or solar radiation. They maintain structural integrity far more effectively over astronomical timescales. Furthermore, their size allows them to potentially preserve a richer, more detailed record of their distant birthplace and the ancient conditions prevalent there. All this potential knowledge is locked within their frozen depths. Adding to its remarkable nature, 3IATLAS traverses the void at an astonishing velocity. It moves with the incredible speed of approximately 210,000 kilometers per hour, equating to roughly 30 kilometers every single second. To grasp the magnitude of this velocity, consider that it surpasses the speed of a bullet fired from a high-powered rifle by a factor of about 70. Such extraordinary speed is not euphemeric. It is the hallmark of an object violently ejected from its native planetary system. This ejection likely resulted from dramatic gravitational interactions with massive gas giant planets, or potentially even a close encounter with a passing stellar neighbor. The violent event that propelled 3IATLAS outwards was forceful enough to send it hurtling irreversibly into the galaxy's vast expanse, forever severed from its point of origin.
Now consider the dimension of time that truly captures the imagination. This solitary traveler has been adrift within the perpetually cold, pitch-black emptiness of interstellar space for an almost inconceivable duration. The minimum estimated time is millions of years, a span stretching back to epochs long before complex life emerged on Earth. It is entirely plausible that its journey extends into the realm of billions of years, a testament to the ancient origins it carries. Throughout this mind-bogglingly long voyage, 3IATLAS has experienced almost no warmth, almost no illumination. Its only sources of light have been the faint, distant glow of stars scattered across the cosmos, while its surface has been subjected to the relentless, constant bombardment of cosmic radiation, a silent, penetrating force washing over it since its departure.
As it drifted aimlessly through the vast emptiness of space, traversing at velocities beyond our full comprehension, its path ultimately led it into the boundaries of our own solar system. However, it was a mere stroke of luck that brought it to our attention, for had the Atlas telescope not been surveying that specific section of the sky on that particular night, 3IATLAS would have soared past us unnoticed, never to be recognized as an interstellar traveler. One can only ponder the multitude of celestial wanderers that have graced our solar system's realm without ever being observed by human eyes. How many celestial entities have traversed between our stars before the invention of telescopes? How many continued to elude our detection due to their diminutive size or lack of luminosity? This prompts a significant inquiry. Should interstellar objects like 3IATLAS be considered rare, or at least infrequently observed? What insights does this provide about the galaxy itself? How many rogue comets and asteroids wander the darkness between the stars? Some scientific minds speculate there could be trillions of these abandoned objects expelled from their original star systems and now adrift within the confines of the Milky Way, each one encapsulating mysteries from the star system in which it originated, each one a temporal capsule hailing from a remote sector of the galaxy. And it is precisely for these reasons that astronomers are so enthralled by 3IATLAS. It hails from beyond our solar system. The gases it emits, the minerals composing its surface, the chemical signatures we may discern all originate from an entirely distinct astronomical setting, a different star, different planetary configurations, and varying environmental circumstances. Imagine the extraordinary opportunity presented by this remarkable celestial visitor. By meticulously studying this comet, scientists are effectively receiving a unique and invaluable sample delivered directly to us from beyond our own solar system's boundaries.
This represents an immense scientific boon. We were spared the monumental challenge and extended timeline of launching a dedicated spacecraft on a journey lasting potentially 1,000 years to reach another star system and attempt sample collection ourselves. Instead, nature itself provided the specimen, bringing interstellar material within our reach for immediate analysis. This inherently fascinating prospect, however, is only part of the compelling reason why 3IATLAS has captured such profound global attention. Beyond the inherent scientific curiosity surrounding this rare phenomenon, there exists a persistent and intriguing question that consistently surfaces during official press conferences, academic research publications, and even informal late-night conversations among astronomers. This question resonates with a sense of underlying uncertainty. Is this truly just a natural comet, or could it possibly represent something fundamentally different, something beyond our conventional understanding? It's natural to wonder if this line of inquiry leads down the well-trodden path of extraterrestrial spacecraft theories, often discussed by less-informed individuals online. However, the nature of this question is distinctly different. Crucially, it is being seriously posed by qualified scientists holding reputable credentials within the astronomical community. They are grounding their inquiry in specific, observable phenomena, gathered by sophisticated telescopes, phenomena that, according to these researchers, present anomalies or inconsistencies that do not readily align with established models for natural cometary behavior. Therefore, it warrants careful consideration before entirely dismissing the possibility. This is not a matter of speculation detached from evidence, but rather a challenge to interpretation based on tangible observations. Before concluding the narrative abruptly, it is essential to understand the developing situation. As 3IATLAS drew progressively closer to our Sun, the detailed data collected revealed an unexpected set of characteristics. These observations defied initial predictions and prompted reevaluation. This critical shift in understanding sets the stage for the intense controversy that is about to unfold. In the following segment, we will delve into this scientific debate, contrasting the prevailing views held by the mainstream astronomical establishment with the strongly expressed opinions of a prominent Harvard University professor.
This professor argues persuasively that the scientific community might be committing a significant error by categorically dismissing the possibility that 3I-ATLAS is not merely a natural object, but something more enigmatic. The revelations emerging from the telescopic data are truly astonishing and demand scrutiny. Thus, our narrative takes a decisive and dramatic turn.
While the broader scientific community was actively engaged in celebrating the discovery of this exceptionally rare interstellar traveler and methodically preparing their instruments and methodologies for detailed study, one prominent voice emerged distinctly from the consensus. This individual offered a highly divergent interpretation, challenging the prevailing assumption that 3I-ATLAS could be explained by conventional natural processes alone. This dissenting perspective has fundamentally altered the course of the scientific discussion. Professor Avi Low, the distinguished chair of Harvard University's renowned astronomy department, possesses a scientific credibility few can match. His career encompasses an extensive publication record comprising hundreds of peer-reviewed research articles, significant advisory roles for the National Aeronautics and Space Administration, and the mentorship of a generation of leading astronomers. Despite having access to the identical astronomical data as his contemporaries, Professor Low arrives at a profoundly divergent interpretation. His perspective challenges established understanding and has sparked considerable debate. The catalyst for this significant scientific discourse emerged with the discovery of the celestial body known as 3I-ATLAS. From the very beginning, Professor Low initiated inquiries that proved deeply unsettling to many of his colleagues within the mainstream astronomical community. His persistent questioning transcended academic circles, capturing widespread media attention globally. Professor Low's central contention revolves around the observed behavior of this object. He asserts that its characteristics do not align with the expected patterns exhibited by a natural comet. Professor Low argues with scientific rigor that, acknowledging the inherent uncertainty within the field, researchers must seriously entertain the possibility the 3I-ATLAS might represent something other than a conventional cosmic phenomenon. He invites examination of his reasoning, which, while ultimately rejected by the vast majority of his peers, presents a compelling challenge worthy of consideration. Professor Low's reasoning rests upon several distinct lines of evidence. Firstly, the object's exceptional luminosity presented a major anomaly. Upon its initial detection, 3I-ATLAS displayed an intensity of brightness far exceeding what would be anticipated for a natural comet situated at such an immense distance from our star. Astronomers conventionally expect comets to remain largely inert until they approach considerably closer to the Sun. The process of cometary activity typically requires sufficient solar heating to penetrate deep into the icy nucleus, triggering the sublimation of frozen volatiles into the characteristic glowing coma and tail.
However, 3I-ATLAS exhibited this glowing activity prematurely, exhibiting near maximal brightness far earlier than physical models predict natural ice vaporization could support. This suggested the presence of an alternative, perhaps artificial, energy source capable of inducing such luminosity at this stage of its journey. Secondly, Professor Low emphasized the remarkable precision of the object's trajectory. He pointed out that the path traversed by 3I-ATLAS through our solar system demonstrated a level of accuracy and mathematical regularity that appeared unusual. Its hyperbolic path and orbital parameters, according to Low, showed an unnatural focus and predictability inconsistent with the typical chaotic or weakly bound trajectories expected of comets originating in the distant Oort cloud, which are generally susceptible to gravitational perturbations from planets. The celestial body's journey unfolded with remarkable precision. Its trajectory was calculated with an uncanny accuracy, positioning it at just the correct angle and at precisely the right velocity. This carefully choreographed path ensured it would pass sufficiently near the Sun to become readily observable from our vantage point, yet deliberately avoided the lethal proximity that would have led to its complete disintegration. Naturally, one could dismiss this remarkable alignment as mere happenstance. Billions of comets are routinely ejected from their parent planetary systems across the vast cosmos. It stands to reason that within this immense cosmic population, some would inevitably find their way into our solar system. Their paths, purely by chance, could intersect ours in a manner that proved fortuitous for our observation efforts. However, a persistent question emerged from these observations. What if this sequence of events was not coincidence? What if the trajectory had been chosen, deliberately plotted rather than arising from random cosmic currents? A second, equally puzzling characteristic captured scientific interest – the conspicuous absence of early, obvious gas emissions. The typical behavior of comets approaching the inner solar system is well documented. As the intense solar heat begins to warm their frozen interiors, these icy bodies usually commence vigorous outgassing long before reaching the Sun's immediate vicinity. One witnesses dramatic jets of gas and pulverized dust violently erupting from their surfaces. Yet this particular object, designated 3IATLAS, exhibited an unusual silence during its initial approach. It possessed significant brightness, confirming its presence and composition, but it lacked the characteristic activity expected of a typical comet. Its behavior was unnervingly stable, almost unnaturally controlled for a celestial wanderer. The sense of unnatural stability deepened significantly as observations progressed. In the month of September, when more sophisticated data became available, this phenomenon was confirmed. The object displayed an unexpected level of structural integrity and maintained a notably high mass. Here lay the critical anomaly. If, as early data suggested, 3IATLAS indeed altered its course slightly during its closest approach to the Sun, a maneuver induced by the powerful solar forces, then an external force must have acted upon it. For natural comets, such a nudge is always provided by the act of outgassing itself. The process is straightforward. Frozen gases and volatiles on one side of the comet heat up more intensely than the other side. This uneven vaporization creates powerful, thrust-like jets, functioning much like miniature rockets. These jets impart a subtle but definite push, gradually altering the comet's trajectory over time. But the mass of 3IATLAS, as determined by the observations, presented a profound challenge to this conventional explanation. The sheer magnitude of its mass suggested that the force generated by typical outgassing jets would have been utterly insufficient to produce the observed course change. When confronting the anomalous trajectory shift of the interstellar object, astronomer Avi Loeb began contemplating a hypothesis that challenged conventional explanations. The core issue was clear. The observed course alteration occurred near the Sun, yet the magnitude of force required exceeded what natural outgassing, the release of gas and dust typical of cometary activity, could physically provide. This discrepancy prompted Loeb to seriously propose technological propulsion as a viable explanation, moving beyond mere speculation to a testable scientific hypothesis worthy of rigorous investigation. In his writings, Loeb articulated this reasoning with precision. He noted that if an object underwent significant acceleration during its solar approach without corresponding evidence of substantial gas emission, the force responsible might originate from artificial means. This could include an engineered propulsion system or even utilize the Sun's radiation pressure via a solar sail. Demonstrating his characteristic blend of scientific rigor and accessible communication, Loeb offered a light-hearted yet pointed suggestion. He humorously advised individuals to consider taking time off work specifically around October 29th, the date the object reached its closest point to the Sun, perihelion, anticipating it might reveal unexpected properties far surpassing initial assumptions. This jest underscored a profound scientific principle. Appearances can be deceiving, and initial classifications based on visual observation, like identifying an object as a comet, must remain provisional until substantiated by comprehensive physical evidence. Predictably, this unconventional hypothesis met with significant skepticism within the established scientific community.
Major space agencies like NASA and the European Space Agency, alongside astronomers at numerous research institutions globally, meticulously re-examined the identical dataset Lowe had analyzed. Their collective interpretation, based on the accumulated evidence, diverged sharply from Lowe's proposal. Crucially, their position was bolstered by compelling observational data. The Hubble Space Telescope captured definitive imagery of the object, revealing a characteristic comet coma. This feature, a diffuse, hazy envelope of gas and particulate matter enveloping the solid core, the nucleus, is a hallmark signature of cometary bodies undergoing solar heating. The presence of this coma provided strong visual evidence supporting the interpretation of the object as a natural comet, directly contradicting the implication of artificial propulsion necessitated by Lowe's initial force imbalance argument. The observed phenomena align precisely with the fundamental behavior expected of celestial bodies composed of frozen volatiles, such as water ice, when exposed to solar radiation. This process causes the sublimation of these materials, releasing gas and dust into space. NASA's SphereX mission, meticulously engineered to investigate the chemical makeup of astronomical objects through their infrared signatures, conducted a detailed analysis of light emanating from the recently discovered interstellar visitor designated as 3IATLAS. Their spectral examination revealed distinct molecular fingerprints corresponding to carbon dioxide, water vapor, and other substances commonly associated with cometary composition. The findings presented no anomalies. Everything detected could be fully accounted for by well-understood natural astrophysical processes inherent to such objects. Further corroboration came from robotic observers already stationed in Martian orbit. During early October of the relevant year, coinciding with the comet's closest approach to Mars at a distance of approximately 30 million kilometers, both the European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter directed their sophisticated imaging instruments toward the approaching body. The resulting pictures captured the unmistakable visual characteristics of a natural comet. A faint, ethereal glow emanating from the nucleus, the developing cloud-like halo known as a coma surrounding it, and absolutely no indicators whatsoever of artificial construction or unexplained energy emissions that might suggest non-natural origins. An observation of particular scientific significance unfolded subsequently. NASA's Swift Observatory, primarily designed for detecting and analyzing cosmic gamma-ray bursts and other high-energy events, was redirected towards 3IATLAS. Its sensitive instruments successfully detected the presence of water vapor within the comet's coma.
This discovery represented a major milestone, marking the first confirmed detection of water vapor specifically from an interstellar comet traversing our solar system. This finding is entirely consistent with expectations for a natural object originating from another planetary system, composed predominantly of ice and rock. Water molecules are pervasive throughout the cosmos, constituting one of the most ubiquitous compounds known. Consequently, their detection within the structure of an interstellar comet is as predictable as encountering sand upon a terrestrial shoreline. The prevailing scientific understanding had crystallized into a clear narrative. Indeed, Oumuamua possessed unique characteristics primarily because it hailed from interstellar space. Its behavior, while intriguing, exhibited certain anomalies. However, these peculiarities did not inherently signify artificial origin. Instead, they pointed towards a comet forged under conditions distinctly different from those within our own solar system. Its underlying chemistry diverged, its internal architecture was unique, and its observable actions reflected this alien provenance. Precisely this divergence rendered Oumuamua an immensely valuable subject for scientific investigation. Consequently, however, an unexpected event reignited passionate debate and triggered widespread excitement across social media platforms. On the 10th day of November, a radio telescope array located in South Africa, the Meerkat Array, registered unexpected radio emissions emanating from Oumuamua. The internet immediately erupted in speculation. Were these emissions signals deliberately crafted? Did this constitute tangible proof supporting earlier assertions about extraterrestrial involvement? Was humanity on the precipice of first contact? The subsequent explanation, while disappointing for those anticipating alien intelligence, proved nonetheless captivating from a rigorous scientific standpoint. The Meerkat telescope had not detected any modulated signal designed to carry encoded information. Instead, what was observed was a natural phenomenon, radio continuum emission occurring at remarkably specific frequencies, precisely 1665 and 1667 megahertz. For those familiar with the field of radio astronomy, these exact numerical values held immediate significance. These frequencies are the distinctive signatures emitted by hydroxyl radicals, OH molecules. These radicals form naturally when ubiquitous water molecules within the comet are subjected to the intense radiation of the sun, causing them to dissociate or break apart. This specific process of water molecule dissociation generating hydroxyl radicals and their characteristic radio emission is a phenomenon observed consistently in comets originating from within our own solar system.
When a comet ventures perilously close to the sun, the intense flood of ultraviolet radiation interacts dramatically with the coma, the vast envelope of gas and dust surrounding its solid nucleus. Within this coma, water molecules, H2O, absorb this energetic radiation, causing them to fragment. This process breaks the molecules apart, yielding individual atoms of hydrogen and radicals of hydroxyl, denoted as OH. These newly formed hydroxyl radicals are inherently unstable. As they transition between various quantum energy states, they release their excess energy in the form of distinct, characteristic radio waves. This sequence of events, the dissociation of water and the subsequent emission of radio waves by hydroxyl, represents a purely natural phenomenon. Astronomers have documented this specific hydroxyl emission signature originating from comets within our own solar system consistently since the 1970s. There is absolutely nothing artificial or indicative of intelligent design involved. It is chemistry and physics operating precisely according to their fundamental laws. However, the detection referenced here carried exceptional significance because it marked the inaugural observation of these specific hydroxyl emissions emanating from an object that originated beyond our solar system, an interstellar visitor. The first such object identified, designated Oumuamua, presented a unique challenge. By the time astronomers comprehensively understood its nature, Oumuamua was already accelerating away, rapidly exiting the solar system before any significant activity, like the generation of a detectable coma, could be observed. The second confirmed interstellar comet, Borisov, followed a different trajectory. Crucially, its closest approach to the Sun remained too distant for the solar heating to trigger vigorous cometary activity. The heat simply wasn't sufficient to liberate large quantities of water vapor from its nucleus, meaning the resulting hydroxyl emission was too weak to be captured by even the most sensitive radio telescopes. The breakthrough came with Comet 3IATLAS. This interstellar traveler descended close enough to the Sun to become significantly active. Solar radiation was intense enough to vaporize substantial amounts of water ice from its nucleus, populating its coma with the necessary water molecules. These molecules then dissociated under the UV onslaught, generating hydroxyl radicals. Simultaneously, astronomers had deployed the appropriate radio astronomy instruments and directed them towards the object at the precise moment it was active. This fortunate alignment of the comet's behavior and human technological readiness meant the data was secured. The scientific value of this collected data is profound.
It reveals a fundamental universality.
The aqueous chemistry witnessed in 3IATLAS, where water molecules break down into hydrogen and hydroxyl under solar radiation, leading to characteristic emissions, mirrors exactly the process observed in comets originating from our own solar system. This demonstrates that the underlying chemical principles are universal, operating identically across the galaxy. Consequently, despite this object having spent potentially millions or even billions of years drifting through the freezing void between stars, its composition aligns remarkably with that of comets native to our cosmic neighborhood. It is constructed from the same primordial materials governed by the same physical laws. This convergence of chemistry, despite an interstellar journey of immense duration and distance, represents a truly profound scientific insight. The fundamental constituents that constitute planetary systems, the diverse collection of ices, rocky material, and complex organic molecules that ultimately aggregate to form planets, and potentially the very foundation for life itself, appear to be remarkably consistent throughout the vast expanse of the galaxy. These essential building blocks, forged in the crucible of stellar nurseries and interstellar clouds, seem to share common characteristics regardless of their specific cosmic location. This observation itself provides a fascinating insight into the uniformity of cosmic processes. However, this understanding illuminates another crucial aspect. It offers a plausible, natural explanation for the peculiar radio emissions detected. There exists no compelling necessity to invoke the presence of advanced alien transmitters or elaborate communication networks to account for the phenomena. The observed object was simply exhibiting the inherent behavior characteristic of its class, comets. It was actively outgassing, releasing volatile materials into space. Within this process, water molecules themselves were being dissociated, broken apart by solar radiation. This fundamental chemical reaction resulted in the emission of radio waves, a natural consequence of basic chemistry operating under the extreme conditions of the vacuum of space. In acknowledging the radio observations, Professor Loeb demonstrated scientific integrity, accepting their validity. However, he steadfastly maintained that hasty conclusions regarding the object's nature should be resisted. He offered a critical and entirely accurate perspective. The detection of these natural radio emissions does not definitively prove that the object is entirely devoid of artificial origin. He presented a hypothetical scenario where an alien probe constructed by an advanced civilization could possess a surface layer of ice. This layer might have been acquired unintentionally during its extended journey traversing the depths of interstellar space.
If such a probe featured this icy exterior, it could potentially exhibit behavior indistinguishable from that of a natural comet. The probe's surface ice could undergo outgassing, releasing water vapor into the surrounding environment, much like a comet nucleus does when heated by the sun. Consequently, observers would detect precisely the same chemical signatures, water vapor, hydroxyl radicals, carbon dioxide, that are characteristic of cometary activity. Yet, beneath this deceptive natural veneer, the fundamental nature of the object could still be artificial, technological, and of extraterrestrial design. At this juncture, one might reasonably feel that the scientific criteria are being subtly shifted, perhaps even moved, in response to new findings. This perception is not entirely unfounded. Nevertheless, Professor Lowe's overarching argument merits serious consideration. He is not asserting with certainty the object known as 3IATLAS is demonstrably an alien spacecraft. Instead, his central point is a call for intellectual humility and methodical rigor. We should refrain from automatically dismissing the possibility of an artificial origin solely because the object exhibits properties reminiscent of comets. The prudent course of action, he suggests, is to maintain an open mind while persistently gathering the maximum possible data through rigorous observation and analysis. Only through exhaustive investigation, he argues, can we hope to reach a sound conclusion about its true and perhaps unexpected nature. Some researchers propose it was merely a fragment of frozen hydrogen, perhaps dislodged from a distant molecular cloud. Others suggest it was the shattered remnant of a planet torn apart by the immense tidal forces near another star. The truth remains elusive, a captivating mystery. Therefore, when someone examines 3IATLAS and advocates for caution against prematurely dismissing alternative explanations, they are drawing a direct parallel to the valuable lesson offered by Oumuamua's unexpected arrival. The cosmos surprised us once with an object whose very existence and properties defied easy categorization. It stands entirely possible, perhaps even likely given that precedent, that it might surprise us again with phenomena challenging our current understanding. However, the accumulated evidence gathered for 3IATLAS, at least to this point, strongly indicates that it conforms precisely to its initial appearance. The data overwhelmingly supports the interpretation that 3IATLAS is indeed a comet, a natural object originating from outside our solar system. It represents, fundamentally, a chunk of ice and rock ejected from another star system's protoplanetary disk millions or billions of years ago, eventually finding itself adrift in the vastness of interstellar space before intersecting with our solar neighborhood. The specific signatures detected, the presence of water vapor, hydroxyl radicals, carbon dioxide molecules, and the detailed structure of the surrounding coma or nebulous envelope, all align perfectly with the characteristics expected from a comet. While acknowledging that it is an unusual comet, specifically an interstellar one whose chemistry reflects the distinct conditions of its extraterrestrial birthplace, the evidence firmly supports its classification as a natural celestial body. The fundamental nature of this celestial traveler remains unequivocally that of a comet, and this very realization, counterintuitive as it may seem, proves to be an even more profound source of excitement than encountering an artificial probe would have been. For the insights garnered from studying 3IATLAS illuminate a universal truth. Planetary systems scattered across the vast expanse of the galaxy operate through remarkably similar processes to those governing our own solar neighborhood. The formation of comets is a common occurrence. Gravitational interactions within these systems frequently propel these icy bodies outwards, ejecting them into the void. These comets then undertake immense journeys across the galaxy, becoming interstellar nomads. Their paths occasionally lead them into the vicinity of other star systems. We are therefore directly witnessing a natural phenomenon, the exchange of material between distinct stellar neighborhoods. Considering the immense scale of cosmic time, operating over billions of years, how many comets have been traded between different stars?
How vast quantities of organic material have traversed these interstellar distances? How many water molecules have been transferred? How many of the essential chemical precursors necessary for life itself have been delivered from one stellar system to another? Although 3IATLAS is not confirmed to be an artificial spacecraft, it nonetheless functions as a cosmic messenger. It carries invaluable information about its distant place of origin. If we exhibit patience and conduct our study with meticulous care, this object can impart knowledge of our galactic environment that would be impossible to obtain through any other means. The narrative, however, does not conclude here. As 3IATLAS pressed inexorably towards the radiant core of our Sun, it began exhibiting behavior fundamentally contrary to the expected nature of comets. Astronomers, previously confident in its natural origin, found themselves baffled by this unexpected development. The comet commenced the dramatic and repeated transformation in color. This chromatic metamorphosis occurred more than once, shifting through hues in patterns utterly inexplicable and defying conventional understanding of cometary behavior.
It is precisely at this point in the story where such profound strangeness emerges that we must now direct our attention. Let us delve into this truly perplexing phenomenon, something so anomalous that even the most seasoned researchers specializing in cometary science were left bewildered. 3IATLAS initiated these startling changes in color, defying all established expectations. Comets are well known for displaying a variety of colors, a phenomenon directly linked to their unique chemical makeup and the intensity of their activity. However, the behavior exhibited by this particular interstellar visitor defied even these established norms. It underwent a remarkable sequence of color changes, a transformation so perplexing that it prompted astronomers to urgently seek answers and explanations. When 3IATLAS was first detected during the month of July, its appearance was distinctly reddish. This initial color was in fact relatively typical for comets situated at great distances from the Sun. The reddish tint generally originates from complex organic compounds residing on the comet's surface. These are sophisticated carbon-based molecules that have undergone significant alteration over immense stretches of time, subjected to the relentless bombardment of cosmic radiation. One might liken this process to a sunburn, though the agents responsible are not ultraviolet rays from our own star, but rather the constant stream of high-energy particles traversing the vastness of interstellar space, gradually altering the comet's outer chemistry. Thus, the red hue initially presented a coherent picture, suggesting this comet had been drifting through the galactic expanse for a truly extended period. Yet in the subsequent month of September, a dramatic shift occurred.
Around the 20th day of that month, astronomers began submitting detailed observations reporting that 3IATLAS had acquired a perplexing green glow. This was not merely a subtle tint. It manifested as a conspicuous, almost ethereal green coloration that became clearly visible in photographic evidence. This sudden development captured the attention of the astronomical community with singular intensity, as green-colored comets are inherently special and relatively rare. The emergence of green light within a comet structure typically stems from specific molecules, diatomic carbon, C2, and on occasion, cyanogen, CN. These molecules are generated when solar radiation breaks apart larger organic molecules present within the comet's diffuse atmosphere, known as the coma. Upon exposure to this sunlight, these newly formed molecules emit a characteristic green fluorescence. Therefore, while the initial red color was expected, the subsequent appearance of green, though chemically plausible, represented a significant and scientifically intriguing transformation for this interstellar object. Comet C 2023-A3 Atlas drew progressively nearer to the Sun, its journey bringing it into warmer solar territory. This increasing heat triggered a significant intensification in its activity. The comet released ever greater quantities of gas into space, fundamentally altering its immediate environment. These released gases created the specific conditions necessary for the formation of those distinctive glowing molecules that make a comet's coma visible. Yet astronomers observed something profoundly unusual unfolding within this process. The comet's transition from exhibiting a reddish hue to a brilliant green glow occurred with remarkable suddenness. This abrupt shift was highly atypical. Most comets display a much more gradual change in color as they approach the Sun, their appearance evolving steadily over weeks or even months. In contrast, Atlas appeared to flip a literal switch. One week its core radiated a distinct reddish light. Within a remarkably short time frame, perhaps just a matter of days or a week, the dominant glow transformed into an intense green. This startlingly rapid color change was so unusual that it prompted deep speculation among astronomers. It led to ask them to question if the internal structure or fundamental composition of this particular comet differed significantly from that of typical cometary bodies. Professor Lowe predictably interpreted this phenomenon as another potential clue suggesting Atlas might not conform to the standard comet model. He noted that such a dramatic and swift color change could signify a sudden, significant alteration in the comet's surface activity, and cautiously suggested, perhaps justifiably, that this change wasn't entirely attributable to known natural processes.
Naturally, the prevailing scientific response took a more conservative stance. Equally predictably, many experts countered, "Hold on,
There's nothing here that inherently demands exotic or unconventional explanations." They argued that comets are complex objects, often possessing layers of material with distinct chemical compositions formed during their early history. As the comet heated up near the Sun, the outermost layers would begin to vaporize and sublimate away. This process of evaporation, they explained, would progressively uncover deeper, previously shielded layers of the comet's nucleus. These underlying strata could possess a different chemical makeup entirely, one that produced the observed green glow more efficiently once exposed. Therefore, while the speed of the color change was unusually rapid, happening much faster than commonly observed in most cometary apparitions, the basic mechanism of different layers revealing different chemistries was considered a plausible, natural explanation for the phenomenon. However, the comet continued to defy easy categorization. In early November, specifically around November 4th according to the calendar, new astronomical images revealed that Comet Atlas was undergoing another dramatic transformation. This time, its appearance shifted once more, this time towards a striking blue color. This development was particularly remarkable because blue comets are exceptionally rare. When a comet does display a blue tint, astronomers generally agree it occurs due to the presence of specific ionized gases. The most common culprit for this ethereal blue haze is ionized carbon monoxide, denoted as CO+, or potentially other similar ionized molecular species. This blue coloration arises from the unique way these charged particles interact with sunlight, emitting light in the blue wavelengths. The emergence of this blue phase, following the previous abrupt shifts, added yet another layer of scientific intrigue to the comet's already perplexing behavior. The comet's dramatic color transformation unfolded as a direct consequence of the relentless solar wind, a continuous stream of charged particles perpetually ejected from our Sun, violently colliding with the comet's diffuse atmosphere, known as the coma. This energetic assault strips electrons from the gas molecules within the coma, a process fundamentally altering the atoms and creating positively charged ions. These ionized molecules subsequently emit a distinctive blue light as they return to their neutral state. This sequence of vivid chromatic shifts, progressing from a dominant red hue through a striking green phase, culminating in a captivating blue color, occurred remarkably swiftly within the span of just a few months. This unexpected and rapid metamorphosis genuinely baffled the scientific community. Their astonishment was not rooted in speculation about extraterrestrial origins, but rather in profound fascination with the intricate chemical processes and dynamic physical phenomena being unveiled.
The paramount question emerged. What specific type of comet could exhibit this particular sequence of color changes? What crucial insights into the comet's internal architecture, its precise chemical makeup, and the distinctions between interstellar bodies and those born within our own solar system did this phenomenon reveal? One compelling hypothesis proposed that each observed color corresponded to a different stratum or layer being progressively exposed and vaporized as the comet ventured closer to the Sun. The initial red surface was theorized to be a radiation-processed outer crust, altered by cosmic rays over extended periods. Beneath this weathered layer lay a green-hued stratum containing pristine, unaltered organic materials, remarkably shielded from the harsh radiation of deep space. Finally, the innermost region, responsible for the intense blue glow, might have been particularly rich in carbon monoxide ices.
These ices would only begin to vaporize intensely when the comet approached sufficiently near the Sun, allowing the solar heat to penetrate deeply enough to reach and activate these specific volatiles. This process was likened to the gradual peeling of an onion, each layer revealing entirely new and previously hidden characteristics. An alternative theory, focusing on the comet's dynamic activity patterns, suggested the color changes stemmed from sudden outbursts, explosive releases of gas originating from specific localized regions on the comet's surface. It was reasoned that if different surface regions possessed distinct chemical compositions, a rapid shift in surface activity from one area to another could produce swift, dramatic changes in the emitted light. Such behavior, characterized by localized outbursts leading to variable emissions, is known to occur in some comets within our solar system. As a comet rotates, specific active regions on its surface become illuminated and heated by the Sun, causing them to activate and deactivate in a rhythmic cycle. This dynamic process results in the emission of material that varies over time, providing a unique window into the comet's composition and formation history. From a scientific standpoint, one particularly intriguing aspect is the correlation between the comet's shifting colors and the story of its origins and the conditions present in its home star system. The presence of red organics on its surface suggests that it has undergone significant processing by radiation over millions of years, hinting at a long and complex journey. Green diatomic carbon hints at the existence of intricate carbon chains, which are fundamental components of organic chemistry, possibly offering clues about the primordial conditions that shaped life's building blocks. Meanwhile, the blue ionized gases point towards volatile substances originating from the outer edges of its planetary neighborhood, where temperatures are low enough for compounds like carbon dioxide to solidify.
When pieced together, these color variations provide astronomers with a layered account of the comet's past, with each hue representing a different epoch in its billion-year saga. Adding to the intrigue, the comet known as 3IATLAS began displaying multiple tails, each with its own unique structure and behavior, transcending the simple textbook depiction of a singular tail. One of these tails exhibited an extremely rare phenomenon, observed in only a handful of comets throughout astronomical history. The initial tail, discernible as a faint streak trailing behind the comet in early October, was identified as the classic dust tail, a stream of minute rock and ice particles propelled away from the Sun due to radiation pressure. The mechanism behind this phenomenon is rooted in the nature of sunlight itself. Photons, while seemingly weightless, carry momentum. When these photons interact with dust grains, they impart a gentle yet persistent force, pushing the particles away and forming the tail's distinctive appearance. Over the course of its journey around the Sun, a comet naturally develops a magnificent, elongated tail. This structure curves gently due to the complex interplay between the dust particles streamlining from the comet's surface and their persistent orbital motion around our star, while simultaneously experiencing the outward push from solar radiation pressure. This phenomenon is a beautiful consequence of celestial mechanics. Then, during early November, precisely on the 8th of November, a truly remarkable astronomical event unfolded. Astronomers observing from Spain, specifically Frank Nebling and Michael Berner, recorded stunning imagery that revealed something extraordinary. Rather than the expected single broad tail, they captured evidence of 4 or 5 distinct jet-like streams erupting directly from the comet's nucleus. These were not the usual wide, soft plumes we typically associate with cometary tails. Instead, they appeared as remarkably narrow, almost columnar rivers of gas and dust projecting outward in startlingly different directions. The visual effect was so dramatic, it evoked the image of an ancient celestial body suddenly being fitted with multiple rocket engines, all firing simultaneously and propelling streams of material into space. It's important to note, however, that while spectacular, this occurrence, though rare, is a documented aspect of cometary behavior. What these observers witnessed were individual jets of gas and dust, each spewing forth from specific vents or fissures on the comet's frozen surface. The mechanism driving these jets is the intense solar heating. As sunlight strikes different regions of the comet's nucleus, it causes localized pockets of volatile ices, primarily water ice mixed with other frozen gases, to vaporize with explosive force.
This pressurized gas escapes violently through surface openings, carrying dust grains along with it and forming these narrow, focused streams. The reason multiple jets became visible at the same time was almost certainly due to the comet's rotation. As the nucleus turned, various previously shadowed, active regions were bathed in sunlight, triggering jets from different vents simultaneously. What rendered this particular observation so significant, however, was the exceptional clarity and definition of the jet structures. While comet jets often begin as sharp streams, they typically disperse and blur into a diffuse cloud quite rapidly as the ejected material expands into the vacuum of space. The images captured on that specific day, though, displayed jets that maintained their distinct, coherent shapes and separation over surprisingly long distances. These columns of material remained discernibly separate from one another for an extended period before finally beginning to merge and fade, a testament to the specific conditions existing within the coma at that moment. Astronomers investigating the enigmatic comet C/2019 Y4 drew parallels to the peculiar characteristics of comet C/16 R2, itself renowned for an exceptionally carbon monoxide-rich composition and the presence of numerous narrow jets emanating from its nucleus. Observational data suggested a striking similarity between the two celestial bodies. This resemblance hinted at the possibility that C/2019 Y4 possessed an unusually abundant inventory of volatile ices, potentially rich in carbon monoxide and nitrogen compounds, fueling its intense activity. Then, precisely 2 days later, on the 10th day of November, fresh imagery unveiled a dramatic transformation within the comet's tail structure. These updated observations revealed the emergence of two distinct and prominent features. The first was a broad, diffuse tail, composed primarily of dust grains, extending approximately 30 arc-minutes away from the comet's central nucleus, or head. To provide a tangible sense of scale, this immense angular span equated to the same size as the full moon observed in Earth's night sky. Consequently, if the tail were visible to the naked eye, it would appear to stretch across a vast swath of sky equivalent to the diameter of the moon itself. This extraordinary length signified a truly active and substantial comet, releasing copious material into space. However, the second feature captured astronomers' imaginations even more profoundly. This was what the scientific community formally identifies as an anti-tail. Despite its seemingly paradoxical name, this phenomenon is a well-understood, though visually arresting effect. An anti-tail manifests as a feature that appears to project towards the sun, directly contradicting the expected direction of comet tails.
It is crucial to understand, however, that this directional appearance is not indicative of material genuinely flowing sunward. Such a physical process would defy fundamental principles of celestial mechanics and solar physics. The phenomenon arises instead from a fascinating interplay between genuine physical processes and a compelling geometric perspective effect. To comprehend this, one must first recall the mechanics behind conventional comet tails. The primary dust and ion tails we are accustomed to observing consistently point away from the sun. This directional alignment stems from the powerful forces exerted by solar radiation pressure and the solar wind, which effectively push the ejected dust and ionized gases outward from the comet's vicinity. However, the ejected dust particles do not simply move in a straight line directly away from the Sun. They continue to follow trajectories dictated by their original orbital motion around the Sun, essentially maintaining the comet's path. Therefore, as the comet journeys through space, it leaves behind a continuous trail of these dust particles. Over time, these particles spread out gravitationally and through the influence of solar radiation, forming a vast, relatively flat plane or cloud of material. This cloud consists of dust particles sharing remarkably similar orbits to the parent comet. The appearance of an antitail occurs due to our specific vantage point and the geometry of this expansive dust sheet relative to the Sun and the comet. When viewed from Earth, the densest concentration of dust within this orbital plane, situated ahead of the comet's current position along its path, creates the compelling visual illusion that a distinct tail-like feature is projecting towards the Sun. This perceived structure is not a stream of actively flowing material. Rather, it is the brightest segment of the comet's extensive trailing dust cloud, aligned in such a way that it appears to point back towards our star. As Earth traverses its own orbital path around the Sun, our vantage point relative to celestial objects shifts continuously. This changing perspective occasionally brings us into alignment where we observe the vast, diffuse sheet of dust ejected by a comet precisely edge-on. In such a configuration, the segment of this dust sheet that physically occupies the region geometrically positioned between the observer and the comet can manifest visually as a distinct spike projecting not away from the Sun, but towards it. This phenomenon is fundamentally an optical effect, analogous to observing the thin edge of a spinning fan rather than its broad, flat plane. Nevertheless, a genuine physical mechanism underpins this appearance. Larger, heavier dust grains released by the comet experience significantly less influence from the Sun's radiation pressure compared to their smaller counterparts.
Consequently, these substantial particles remained clustered much closer to the comet's actual orbital trajectory, rather than being swept dramatically backward. The striking sunward-pointing spike we perceive, therefore, arises from our specific viewing angle, aligning our line of sight with this concentration of relatively massive, less deflected dust particles streaming along the comet's path. The antitail observed in the comet 3IATLAS was measured to extend approximately 10 arc-minutes in length, representing a dimension roughly equivalent to 1/3 the diameter of the familiar lunar disk. This scale underscored the phenomenon's substantial nature. The very visibility of this antitail revealed critical information to astronomers. Firstly, it confirmed that the comet was generating an immense quantity of dust, sufficient to form a discernible concentration of these larger particles. Secondly, it demonstrated that Earth's position at that specific moment provided the optimal viewing geometry required to capture this rare optical effect. Thirdly, the presence of a sufficiently broad and extensive dust sheet capable of being observed edge-on indicated that the comet's dust production had been consistent and sustained over a significant period, allowing material to accumulate and spread across a wide area. This analysis drew the attention of Professor Lowe, who nonetheless offered further commentary. He observed that the intricate jet structures feeding the dust were strikingly well defined and exhibited remarkable persistence over time. Based on this observation, he proposed a speculative, though highly cautious, interpretation. He suggested, carefully framing the idea, that if such precisely directed jets were indeed evidence of artificial propulsion, they could theoretically be harnessed for course correction by an extraterrestrial operator. This hypothesis, however, remained purely conjectural and was presented as a thought experiment rather than a proven fact. The researcher meticulously chose his words, ensuring he did not assert the phenomenon was artificial in origin.
His intention was simply to illustrate the hypothetical appearance of spacecraft propulsion achieved through the controlled release of gases, should such a method ever be employed. By this stage, however, many astronomers found themselves unconvinced, their skepticism often visible in their expressions. It was undeniable that the jets emanating from the object were visually arresting. Their organization was equally striking. Yet, such formations are not entirely without precedent in the natural world. Comets, of their own accord, can generate these collimated jets. This process occurs when subsurface gases, building pressure beneath the comet's protective outer layer, discover a point of weakness. These fissures or vents in the crust provide an escape route.
The pent-up force then erupts in focused streams, much like the sudden release of steam from a pressure cooker equipped with a safety valve. No human intervention or technological manipulation is necessary to explain this dramatic display. Still, one must concede the powerful impact of the imagery captured. Observing this interstellar traveler blazing with an ethereal blue light, sporting multiple luminous tails and jets, with an anomalous spike seemingly directed towards the solar source, indeed evoked a profound sense of the alien. This alien nature, however, did not imply extraterrestrial engineering. It signified the utterly foreign and exotic quality of the spectacle, unlike any phenomenon most observers had previously encountered. This very strangeness, this defiance of conventional cometary behavior, formed a significant part of the reason why 3IATLAS seized the public's imagination so completely. There exists a deep-seated, visceral attraction to witnessing a celestial object that acts in ways fundamentally different from expectations. It triggers a powerful response, a surge of wonder, that persistent feeling that perhaps, just perhaps, there might be more to the unfolding scene than established textbooks and conventional scientific models prepared us for. Even when every single observation is fully accounted for and explained through well-understood principles of physics and chemistry, the experience remains profoundly remarkable. And indeed, it was remarkable. This remarkable object belonged to a distant star system, forged under conditions entirely alien to our own solar environment, around a celestial body whose identity may forever remain unknown. It carries within its very substance unique chemical signatures, silent witnesses to the distinct primordial conditions of its distant birthplace. Now, this interstellar traveler graces our vicinity, performing an extraordinary spectacle of light, a cosmic broadcast transmitting its intricate composition and dynamic activity patterns across the entire electromagnetic spectrum. Anyone equipped with the proper instruments, a telescope to capture its image, and a spectrograph to analyze its light, could witness this phenomenon. The subtle shifts in its hue revealed vital information about its stratified internal structure and the radiation it had endured throughout its long journey. The appearance of multiple energetic jets offered profound insights into its internal makeup and the nature of its ongoing activity. The presence of the elusive anti-tail provided crucial clues about the specific geometric relationship between our observing perspective and the distribution of dust particle sizes within its coma. Each fragment of data gathered became another vital clue, another distinct piece falling into place within the complex puzzle of how comets operate, not merely within our own solar system, but potentially throughout the vast expanse of the galaxy.
The scientific observations, however, were far from complete. The comet, designated 3IATLAS, was rapidly approaching the critical threshold of its passage through our solar system. On the 29th day of October, it would attain perihelion, the point in its elliptical path where it comes closest to our Sun. That moment heralded a profound transformation. The true crucible awaited. Would this visitor from the depths of interstellar space survive its harrowing brush with the Sun's intense heat and powerful gravitational forces? Or would it disintegrate, shattered by the combined effects of tidal stresses and thermal shock?
The outcome would yield invaluable information about the fundamental structure and composition binding this comet together. The answers were imminent and would undoubtedly astonish the scientific community. Before delving into the critical events surrounding perihelion, it's essential to discuss a fundamental characteristic of interstellar objects that most observers fail to appreciate. For eons, this celestial traveler traversed the silent, star-strewn expanse, enduring a relentless transformation orchestrated by one of the universe's most formidable agents, galactic cosmic radiation. Within the vast, unprotected vacuum lying between the luminous spheres of stars, there exists no shield against this cosmic assault. No protective blanket of atmosphere, no fortifying magnetic field offers respite. Only raw, unfiltered exposure to the ceaseless torrent of the galaxy's most potent energy. High-speed galactic cosmic rays, comprising energetic protons and even heavier atomic nuclei. These particles, accelerated to velocities approaching the cosmic speed limit by the cataclysmic explosions marking the deaths of massive stars, the supernovae, stream through space. Far from merely passing harmlessly through matter, these hyper-energetic invaders violently collide with any obstacle in their path. Their impact is devastating on the molecular scale, shattering complex carbon-carbon bonds and fundamentally rearranging the very atoms that constitute matter. This process profoundly alters the chemical composition of anything subjected to its fury. For the comet designated 3IATLAS, this prolonged bombardment endured in unimaginable duration, potentially spanning not just millions, but tens or even hundreds of millions of years. Each day, without respite, this cosmic rain of particles pounded against its frozen surface. This relentless assault continuously broke down existing molecular structures and forged entirely new chemical compounds. Over geological epochs, this created a distinct radiation-processed outer crust upon the comet, a feature utterly alien to the composition observed in comets originating within our own solar system. Then, in the 11th month of recent observation, scientists received definitive confirmation of the extremity of this transformation.
Spectral analysis revealed that the internal makeup of 3IATLAS diverged significantly from the norm of familiar cometary bodies. It contained substantially higher concentrations of carbon dioxide and carbon monoxide than anticipated. This specific chemical signature provided the smoking gun evidence for the profound effects of radiation processing accumulated over immense timescales. Over millions of years, this continuous exposure fundamentally rewrote the comet's chemical identity. The most astonishing revelation, however, stemmed from scientific estimation regarding the depth of this altered layer. Scientists calculated that the surface might be shielded by a crust formed through this radiation bombardment exceeding 20 meters in thickness. 20 meters of material subjected to the corrosive effects of cosmic rays for eons. This staggering depth implied that the surface layer, currently visible to astronomers, might bear no resemblance whatsoever to the primordial, unaltered composition that existed deep within the comet's core. The pristine material from the comet's birth star system could still be locked inside beneath that radiation-baked crust. And that's exactly what perihelion might do. When a comet gets close to the Sun, intense heat can crack the surface crust, exposing fresh material from deeper layers. If 3IATLAS experienced enough thermal stress, that 20-meter crust might crack open, revealing the untouched ice beneath. So October 29th wasn't just a date on the calendar, it was the moment of truth.
The comet reached perihelion at 136 astronomical units from the Sun, about 204 million kilometers, roughly between Earth and Mars. Close enough for the Sun's heat to have a major effect. And the effect was immediate and dramatic. 3I/ATLAS suddenly brightened, its magnitude jumping from around 12 to approximately 9. That's roughly 15 times brighter in a very short period. That kind of sudden brightening usually signals a major outburst, either from fresh ice exposure or the comet breaking apart. Telescopes tracked the comet during this critical period. The images showed something beautiful and eerie. The comet appeared unusually blue from ionized gases. The solar wind was slamming into the expanding coma with incredible force, creating a glowing blue halo around the nucleus. Spectroscopic analysis detected carbon dioxide and NH2 amino radicals, formed when ammonia breaks apart. This was new, suggesting that fresh ammonia ice buried beneath the surface was now being exposed. The heat from perihelion had indeed cracked the crust. The collective anxiety reached its peak with a single, haunting question. Had the comet truly endured its perilous passage near the Sun, or had it shattered beyond recognition? For nearly a full week, a palpable atmosphere of doubt lingered.
This was due to the comet's temporary position directly behind the Sun from our viewpoint on Earth, rendered invisible by the overwhelming solar glare. Our only glimpses came from orbiting solar observatories, yet their observational clarity proved insufficient. They could not deliver a definitive verdict on whether the comet's core remained whole or had fractured into scattered debris. Professor Lowell seized upon this profound uncertainty. On the 11th day of November, he posed the crucial query directly. Has 3I/ATLAS simply disintegrated near the Sun? He highlighted the presence of distinct jets and streamers emanating from the comet, features that could be interpreted as signs of fragmentation. However, his analysis contained a more provocative counterpoint. He reasoned that if the object emerged intact after its closest approach to the Sun, this would demonstrate an extraordinary level of structural robustness. Such resilience, he suggested, might even surpass that of a typical comet nucleus, which is often perceived as fragile. As the comet, designated 3I/ATLAS, ventured outward from the Sun's intense proximity, a fresh enigma captivated the scientific community. Suddenly, the paramount question shifted away from mere survival. Researchers found themselves intensely debating whether the comet's fundamental path had undergone a profound alteration.
This line of inquiry stemmed from a fundamental principle of celestial mechanics: the overwhelming gravitational pull and the powerful pressure of solar radiation encountered during such a close solar approach possess the remarkable ability to subtly warp an object's trajectory. The gravity well of our star could literally bend the comet's flight path, while the relentless stream of photons exerted a minuscule yet significant outward push. It was this potential for such profound gravitational and radiative influence to induce deviations that prompted a more unsettling line of thought. If the comet's actual flight deviated substantially from predicted models in ways that defied conventional explanation, then perhaps Professor Lowy's long-dismissed notions about artificial propulsion mechanisms embedded within the comet could no longer be comfortably ignored. The solar flyby of 3I/ATLAS did indeed yield astonishing observations. Astronomers precisely measured the bending of starlight passing near the Sun as the comet traversed the region, an effect known as gravitational lensing. The degree of this bending, astonishingly, matched Einstein's theoretical predictions with remarkable fidelity, registering precisely 1.75 arcseconds. This stunning confirmation of relativity theory occurred alongside another, more unexpected finding. While the gravitational lensing aligned perfectly,
The comet's own measured trajectory deviated from standard orbital calculations by an entirely different amount, 4 arcseconds. In the highly precise domain of orbital mechanics, where measurements are scrutinized to the finest degrees, such a discrepancy was neither negligible nor easily dismissed. It demanded rigorous investigation. The most straightforward and widely accepted explanation for this observed deviation lay in the well-understood phenomenon of radiation pressure. Sunlight, though seemingly gentle, exerts a tangible force upon all objects it strikes. For a celestial body as lightweight and fragile as a comet nucleus, this constant, gentle push from photons could indeed accumulate over time, nudging its orbit measurably. Furthermore, comets are notoriously active entities. They frequently expel gas and dust in powerful jets as solar heating causes sublimation of ices beneath their surfaces. The pattern of this outgassing is rarely symmetrical. It often occurs in distinct organized jets erupting from specific regions on the comet's surface. This asymmetric outgassing, acting like a natural thruster, combined with the consistent push from radiation pressure, produced a combined effect capable of altering the comet's trajectory. The resulting deviation, calculated using established physical models incorporating these factors, fell comfortably within the realm of normalcy observed in other cometary encounters with the Sun. It was a plausible, conventional explanation.
However, Professor Lowe, known for his persistent and often controversial hypotheses, offered a markedly different perspective. He acknowledged the power of radiation pressure and asymmetric outgassing as natural causes, but challenged their sufficiency. He drew attention to the strikingly well-defined and persistent nature of the jets observed on 3IATLAS during its solar approach. These weren't chaotic, random bursts of activity. They appeared remarkably structured and directional. Professor Lowe suggested that this specific pattern of outgassing might not be entirely random or purely driven by natural thermal processes. He proposed a more speculative yet tantalizing possibility. What if the internal structure or composition of the comet itself was engineered to produce this particular, highly efficient outgassing pattern? If so, the resulting net force generated by the jets could be directed in a specific way, potentially creating a sustained thrust that could alter the comet's trajectory in patterns that appeared suspiciously precise or even purposeful, thereby mimicking the subtle effects of artificial propulsion. This idea, while lacking direct evidence, forced the scientific community to reconsider the boundaries of possibility when observing such intriguing celestial phenomena. The scientific community's response to recent observations was unambiguous. Scientists emphasized that asymmetric outcasting represents a common phenomenon observed in celestial bodies traveling through the solar system. Comets frequently possess irregular, lumpy shapes and varied surface features, such as cracks, vents, and dark crusts. These unique structures naturally channel released gases, primarily water vapor and other volatiles, outwards in specific, unpredictable directions. This directional jetting effect has been documented in dozens of comets over many years of astronomical study. Consequently, nothing truly unusual was detected in the current observations of the object in question. However, a significant limitation to absolute understanding remains. Scientists acknowledge that definitive confirmation of the exact mechanisms causing the observed activity might be unattainable. The object, designated 3IATLAS, possesses a destiny that will ultimately carry it beyond our ability to study it closely. Its journey is set to conclude dramatically. By the 19th day of the 12th month in the year 2025, this comet will reach its point of closest approach to Earth. At that critical moment, it will be situated at a distance of 1.8 astronomical units away, a measurement equivalent to approximately 269 million kilometers.
Following this, by the third month of 2026, 3IATLAS will traverse beyond the orbit of the great gas giant Jupiter.
Finally, entering the early years of the next decade, specifically the early 2030s, it will depart completely from the region encompassing our solar system's planets. It will return to the vast, dark expanse of interstellar space, vanishing once more into the cosmic ocean from which it originally came. For those viewing this information during the late period of November in the year 2025, a unique opportunity arises. There is a chance to directly observe 3IATLAS themselves using appropriate equipment. Observers possessing a telescope with an aperture between 80 and 150 millimeters, combined with observing from locations experiencing truly dark skies, should be able to spot the comet. Currently, it occupies a position within the constellation named Virgo. It remains visible in the pre-dawn sky, observable roughly 90 minutes before the sun ascends above the horizon. The optimal viewing window occurs during the final weeks of November 2025. Observers must, however, exercise caution regarding the moon's position. The period around the 19th of November features a new moon, providing perfectly dark skies ideal for observation. Conversely, the full moon occurring on the fourth day of the 12th month will flood the sky with light, completely obscuring the comet's faint presence. When observed, the comet will appear simply as a small, faint, fuzzy glow. Its visual spectacle is not considered spectacular. Yet one must contemplate the profound nature of the object being viewed. This is an entity originating from another star system, having traversed the immense distances between stars for millions of years solely to reach this singular moment within our solar system. This simple act of seeing connects us across unimaginable expanses of space and time, a connection that profoundly transcends the comet's modest visual appearance. Several common questions frequently arise regarding this phenomenon. Addressing these directly, could 3IATLAS pose any danger? The answer is unequivocally no. The closest approach distance is 269 million kilometers. This distance is nearly twice the average separation between Earth and the Sun. Given this immense gulf, there exists absolutely no probability of collision with our planet. Is it truly of extraterrestrial origin? Indubitably, the object's hyperbolic trajectory unequivocally confirms its alien provenance. Could it possibly harbor the unmistakable signatures of an extraterrestrial spacecraft? Almost certainly not. Each and every observation, from the detection of water vapor and carbon dioxide to the intricate details of its dust composition, coma, and tails, all align seamlessly with the characteristics of a natural comet. What distinguishes 3IATLAS from its predecessors?
It stands as the third confirmed interstellar visitor to our neighborhood, and crucially, we have been afforded both more time and access to superior instrumentation to scrutinize it in comparison to earlier interlopers. Through this meticulous examination, we have gleaned profound insights into the resilience of interstellar comets, discovering that they can withstand journeys spanning millions of years. Moreover, we have uncovered that cosmic radiation sculpts a thick crust upon these celestial wanderers, and most intriguingly, that the fundamental building blocks of planetary systems share remarkable similarities across diverse stellar environments. Reflecting upon this captivating narrative, 3IATLAS presents itself unequivocally as a comet, a natural entity dislodged from its home planetary system billions of years ago, and devoid of any trace of artificiality or extraterrestrial origin. However, this revelation in no way diminishes its awe-inspiring nature. What we are privileged to witness is a natural phenomenon occurring ubiquitously throughout the galaxy. The formation of stars, the birth of planets, the genesis of comets and their subsequent trajectories propelled by gravitational interactions, sending them adrift through the cosmic expanse. The galaxy is teeming with these drifting ambassadors from distant suns. 3IATLAS serves as a poignant reminder that we inhabit a universe intrinsically interconnected. Over the eons, matter traverses, disseminates, and intermingles. The question arises, how much material has been exchanged between star systems? And how many organic molecules have been dispersed across the galaxy by comets such as this? Ponder upon the notion that some of our own stardust may have originated from the farthest reaches of other star systems. Therefore, if your circumstances allow, seize the opportunity to witness Comet 3I/ATLAS within the forthcoming weeks. Contemplate the extraordinary odyssey the celestial traveler has undertaken to reach our vicinity. This singular encounter might represent the sole occasion throughout all human history that we, as observers, witness this specific object. It emerged from the profound unknown, briefly traversed the illuminated expanse of our solar system bathed in sunlight, and now retreats back towards the encompassing darkness, destined never to grace our skies again. Before concluding this reflection, consider this. If the tale of this fleeting visitor has ignited your curiosity, allow this moment to inspire a deeper engagement with the unfolding story of our universe. Space science advances with remarkable velocity, and it is our shared endeavor to remain informed about these astonishing revelations. Should this exploration have captivated you, we invite you to join the ongoing journey of discovery. Share this experience with anyone whose spirit is drawn to the mysteries of space and the cosmos.
Comet 3I/ATLAS currently journeys through the void, carrying its unique secrets away beyond our reach. We have had our brief moment with it. We have gleaned what we could from our observations. The story it wove, the profound questions it raised, the sheer wonder it evoked, these are the legacies that remain etched within our collective memory. Perhaps in the distant future, another civilization, situated light years away, will detect its presence as it passes through their own stellar system and ponder the very same mysteries. That, in essence, constitutes the enduring legacy of Comet 3I/ATLAS. It transcends the valuable scientific data collected. It serves as a powerful reminder of our interconnectedness. We are all threads within a vast cosmic tapestry, bound together by the fundamental matter that flows through the galaxy, unified by the insatiable curiosity that compels us to look upwards and relentlessly ask, why? Continue to gaze upwards, continue to pose questions. The universe holds countless more visitors and enigmas in store for us, waiting to be discovered. Until our next encounter with the cosmos, may your skies be clear, and remember this fleeting moment. Look for our transient guest while you still have the chance.